This session, pretty easy. I think it's about probably junior level, and so we go through it fairly quickly. I think you'll have no trouble following it. So you probably notice the intellectual level varies somewhat. Sometimes it's up at master's level, sometimes senior level. Now I think this is junior level, so not too hard. All right, now, as I was saying towards the end of the last session, so now we have a second arrow and this new thing. So without the stack, just this, and without the second arrow, that's the kind of finite automaton we've been used to. Well, now you have a push down automaton, meaning you have a stack, and see this wiggly line here. That's to indicate that this stack can go down effectively forever. Right? Its depth is infinite, so it's not a finite automaton at all, right? By adding the stack. Now, so a PDA, so a push down automaton. What does it do with a stack? Well, it can write symbols onto the top element, the top position of the stack. So in this case, X here is the top element of the stack, and the second top is Y, third top is Z, and so on. So now, before X got put here, now to put an element on the stack, the verb is push. So you push the stack. Okay. So for X to be here, that means previously that X was pushed onto the stack. Right. Now, before that happened, Y was pushed onto the stack, and before that Z was pushed onto the stack. Okay. Now you can then later, once X is there, once the top symbol, the symbol at the top position of the stack, once it's there, then you can read it later. So you may read the element on the stack, and what that means is that you read the element, the symbol at the top of the stack, and that's all you can do. With stacks, you can only read the top element, and you can only pop. Pop is to remove X. So if you removed X, then Y and Z, it's a stack, right? Imagine the set of plates, a stack of plates with a spring underneath. And so if you take off one plate, and that'd be equivalent to taking off the X, the top element, the top symbol, then all the others sort of move up one. Okay, there's like the analogy with the plates. If you remove the top plate, there's less weight in the stack, so there's less weight on the spring. So the spring expands a little bit and pushes up the plates. So the plates pop up a little, one position. So you remove X, and then all these other ones underneath move up, and then Y would then be the element at the top of the stack. Okay, and if you pop it again, then Z would be the element at the top, the symbol at the top of the stack, and so forth. Okay. Now that's what I've just been saying here. So you're familiar now with the concept of pushing and popping, those two verbs in relation to stacks. I'll just say it again. To push means to put a symbol at the top of the stack. So if you had the symbol X and you push it onto the stack, the Y was here and the Z was here, but those two now, and all the others below them, all of them get pushed down one position in the stack, and then you have this is now empty, and you put the X in the top position. All right. That's pushing, and popping is the opposite. When you pop the stack, your top one is removed, and all the others move up one. So if you pop that X, this Y would now move up to here, and the Z would move up to here, and so on. Okay, so that's popping, pushing and popping. Now, Yeah, that's what it's saying here. Now, so you can look on a stack as a kind of, it's a storage device, right? So it's a memory, because you're putting symbols on the stack for later use. So it's a memory device, and it's called a LIFO, L-I-F-O device, or equivalently, because it's the same idea, a FILO, F-I-L-O device. Now, by LIFO, if you look at this, the last one in, the last one to push onto the stack, in this case was X, but that's the first one out, right? So last in, first out, L-I-F-O, LIFO. Or if you looked at, let's say Z is the bottom, like the earliest one to be pushed. So just common sense. You've got to pop these ones above it before Z can be popped. Okay. So it was the first one in, let's say, so it'll be the last one out. So first in, last out, F-I-L-O, FILO. Okay? So FILO. So FILO and LIFO, sort of, they're equivalent. Okay? So a stack is a LIFO, or FILO, memory device. Make sense? Now, common sense, sort of fairly obvious. If you write onto the stack, in other words, you push the stack, and you do it several times, then the information, the symbols that are stored lower in the stack, you cannot access them directly. You can only get at them, read them if you like, or pop them, if the symbols above that symbol you're talking about, that you're trying to access, you can only get at it, you can only access it if the symbols above it are already popped. In other words, you can only access the symbol that's at the top of the stack. Right? That's important. Right, now here, well, it's just, I've already said it several times, that's just giving you the analogy with the plates, like a stack of plates and the spring underneath. So when you push the stack of plates, you add another plate, and the weight of the stack will push compress the spring, so the whole stack will go down one, so to speak, right? And popping does the opposite. You take off the top plate, which is analogous to popping the stack. In other words, taking off, reading and taking off the top symbol on the stack, and so then all the others move up one position, sort of like the plates, right? Now, why are stacks valuable? Well, their infinite depth makes them very valuable. Okay, so that means that a push-down automaton, a PDA, can do things that a finite automaton, like a DFA, cannot do, because the critical word is F, finite. A DFA has finite memory. It has a finite number of states, okay? And it has no stack. Okay, so DFAs are limited in what they can do, and a PDA can do more because it has effectively infinite memory. A stack can be infinitely deep. Right? That's sort of what's saying here. Now here's an example of this is a non-regular language. Remember, we've done that before. Because the strings in this language are of this form. You have n zeros followed by n ones. So the same number of zeros, same number of ones. All the zeros on the left and all the ones on the right. So all the strings of that form, they form this language. That language cannot be recognized by a DFA, because you'd need infinite memory to be able to count the number of initial zeros. But a PDA can recognize it because its stack is infinitely deep. Okay, so it can count it. It can actually count the number of zeros in the string. And well, I end this session and the board with a question. How does a PDA recognize this language here? You can probably guess how it's done. But the point is, this PDA can recognize this language because it has infinite resources. It has an infinite memory. Its stack is infinitely deep, right? You can store an infinite number of symbols. There's like this n here is unlimited, right? It could be as large as you like. Whatever n is, the stack can handle it, right? It's unbounded, right? That's what I've been saying here. Okay, so I'll leave you with this tantalizing question. How would you use, so we have not yet discussed how a PDA works. How do you use pushing and popping of a stack to perform some task, to recognize some language. So here's our first example of the use of a PDA, and here's a language. It's a non-regular language. There is no DFA that can recognize it, but this language can be recognized by a PDA, push-down automaton, a stack-based machine. Okay, so think about how to recognize this language. Okay, ciao.